Welcome back. In this video, we discuss eigenfunction expansion in terms of the eigenfunctions of regular Sturm-Liouville problems. In order to discuss eigenfunction expansion, we'll need to review exactly what a regular Sturm-Liouville problem is. We'll discuss two additional properties of the eigenvalues and the eigenfunctions, which we're calling lambda sub n and f sub n, of regular Sturm-Liouville problems. And then after that, we'll do an example. And I'll probably make a second video with a second example of these for those that don't need the background. Okay, so here's the background. Here's a regular Sturm-Liouville problem. And we'll abbreviate that S-L. A regular Sturm-Liouville problem is a boundary value problem. If a differential equation, the second order ordinary differential equation, can be written in the following form: P times F prime plus Q times F plus lambda times sigma times F equals 0 for x between A and B, where lambda of x is positive on the interval of interest, and of course, P or Q and sigma here are continuous, and P has to be continuously differentiable. If we have that as our second order differential equation, and we've got these two boundary conditions, kappa sub 1 times f of A plus kappa sub 2 times f prime of A equals 0, and kappa sub 3 times f of B plus kappa sub 4 times f prime of B equals 0, then what we have is a regular Sturm-Liouville problem. These functions P, Q, and sigma will be given. The function that we're looking for, the solution to this boundary value problem, will be the function f here. That's the unknown function in this differential equation. Now, there's also a parameter lambda, and those are real values that correspond to specific solutions to the boundary value problem. So whenever we have something like this, our goal is pretty much just like whenever you're solving an initial value problem, your goal is to find the infinitely many non-zero, mutually orthogonal solutions to the boundary value problem, and corresponding values of the parameter lambda. Those solutions are called f sub n of x, or notated that way. It's just f of x, but we're including this subscript n because we're going to have infinitely many of them. Those solutions are called the eigenfunctions of the regular Sturm-Liouville problem. And those values of the parameter lambda are labeled lambda sub n, again, because we've got infinitely many of them. We have a sequence of them. Those are called the eigenvalues. Every eigenfunction corresponds to a particular eigenvalue. Okay. So this video is about two additional properties of these eigenfunctions and eigenvalues. In earlier videos, we talked about theorem 3.8, which said that as n goes to infinity, the lambda sub n go to infinity, that we have an infinite sequence of the lambda sub n, and that infinite sequence is increasing, and that the eigenfunctions that go with the eigenvalues are mutually orthogonal, meaning that if we multiply them together and we also multiply by this weighting function, sigma of x, and then we integrate over the interval from a to b, we get 0 for any two functions in this list of eigenfunctions that are not identical to each other. So here are two additional properties. The first is something I think I've said many times, but haven't actually stated as a property. Only one linearly independent eigenfunction. Oops. Oh, that independent is right. F sub n exists for each eigenvalue. Eigenvalue, there we go. Get one function for each eigenvalue, and then the next property is this. It's a very important property. The set of eigenfunctions, starting with n equals 1 and going to infinity, is complete. What that means is that any piecewise smooth function u defined on the interval from a to b has a unique generalized Fourier series expansion or sometimes it's called just an eigenfunction expansion. Of the following form. And we use a tilde there because they're not always equal to each other. They're only equal at the points where this function is continuous on the interval from a to b, this function u. But if we expand this, we see that this is c sub 1 times f sub 1 of x plus c sub 2 times f sub 2 of x plus c sub 3 times f sub 3 of x. We've done something very similar to this before whenever we came up with Fourier series expansions for functions. But now we're saying we don't have to use just sine and cosine functions with different frequencies. We could use any eigenfunctions. We can use any eigenfunctions, or in particular, we can use the eigenfunctions that correspond to solutions of regular Sturm-Liouville problems. And that's pretty nice. So basically, we can take any piecewise smooth function on that interval. If we have a set of eigenfunctions that is a set of solutions to a regular Sturm-Liouville problem, we can use those as the building blocks for some other function. And we'll just take a weighted combination of those where c sub 1, c sub 2, c sub 3, those are just your constants or the weights. If we take a weighted combination of those eigenfunctions, we can get any piecewise smooth function that we want, almost. When I say almost, it's because of the convergence of this series expression over here. So let's talk about convergence now. And the series on the right converges pointwise to this expression, and I'll talk to you or we'll talk a little bit about what this expression means. This is just talking about the limit of u of x as we approach a particular x value from the right. And this is the limit of u of x as we approach a particular x value from the left. We're taking those that we add those two limits together and then we divide by 2. So we're taking the average of the limits from the left and the right at each x value. And then we're saying this series will converge to that average whenever the function is discontinuous. If the function is continuous, the limit on the left and limit on the right are going to be the same. And so you're just going to get the value of the function there. So this is just saying that if we do have a piecewise smooth function, that means it's going to have a finite number of jump discontinuities on the interval from A to B. And anywhere where it's discontinuous, this series will converge to the average of the limit from the left and the right. And that's what that notation tells us. So this is converging pointwise to this for x between A and B. In particular, it converges to u of x when u is continuous, or converges to u of x if u is continuous at a particular x value. That's nice. So that means we don't just have to use those sine and cosine functions of different frequencies. We can use any building blocks that we want, provided those, or we can use any set of eigenfunctions that we want. The sine and cosine functions of different frequencies do correspond to solutions of a regular Sturm-Liouville problem. So those are just special cases of this. This is exactly the same thing. It's just more general. If we've got a set of eigenfunctions, we can find this particular expansion for a function u of x, provided that u is piecewise smooth on the interval from A to B. Okay, if you're saying to yourself, how do I find that? You find it in pretty much the same way that you found the coefficients for a Fourier series. So you're going to know the eigenfunctions f sub 1, f sub 2, f sub 3. You already have that set. You're just trying to find the constants c sub 1, c sub 2, and c sub 3. To find those, you're going to first treat this equation, which is equation 3.9 in the text, or this expression. We're treating it formally as an equality. We're saying, okay, assume that those are equal. And then if you want to find the c sub n, you just multiply by the weighting function, sigma of x, and an eigenfunction with a different value of that index. So we say we'll multiply by sigma of x and f sub m of x. And then we'll integrate over the interval from A to B. When we do that, because the f sub n of x form an orthogonal set where any two of those functions are going to be orthogonal with weight sigma, then we'll be able to cancel almost all of these. We're going to have an infinite series on the right. I'm going to be able to cancel most of those except for one, exactly one. And that will allow us to solve for the c sub m. So let's write that down. This all stems from the fact that this is an orthogonal set so f sub n and f sub m are orthogonal with weight sigma. Since all that's true, and it'll allow us to find the c sub n. All right, so that's the plan. Let's look at our first example. So this is the example. It says, consider the regular Sturm-Liouville problem given here. We have a differential equation. We know that x is between 0 and 1. When x is between 0 and 1, we have f satisfying this differential equation. Lambda is a value of a parameter. We're calling those the eigenvalues of the Sturm-Liouville problem. And we know that f of 0 equals 0 and f of 1 has to be 0. And it turns out that if you solve this regular Sturm-Liouville problem using the methods that we've discussed in other videos, you can find that the eigenfunctions that satisfy this are f sub n of x equals e to the negative x times sine of n pi x for n equals 1, 2, 3, and so on. Then we're asked to construct the generalized Fourier series expansion, or otherwise known as the eigenfunction expansion, for the given function u and the eigenfunctions above. Okay, so one of the first things that we have to do anytime we are given a regular Sturm-Liouville problem and its eigenfunctions, and then we're asked to expand a given function in terms of those eigenfunctions, one of the first things we have to do is identify the weight. We talked about that just a moment ago. We have to multiply by this weight sigma of x, as well as f sub m of x. F sub m is easy to find, just replace the n with an m, but we have to find the weight that corresponds to the particular regular Sturm-Liouville problem. And that means that we need to write the differential equation in this form. Now, as it stands right here, the differential equation is not yet in this form. This is supposed to have an f prime times a function p, and that quantity is supposed to be differentiated. We're supposed to take, the prime of that, or we're supposed to differentiate that expression. And we don't have that. This is just supposed to be an f, and that's supposed to be an f, and we're supposed to have p times f prime prime. And I've got an f double prime and an f prime right here. So we need to first rewrite this expression, or write the differential equation. Oops. In the form pf prime prime plus q times f plus lambda times sigma times f equals 0, so that we can identify sigma. And we need to be able to identify sigma so that we can multiply by it and then use the orthogonality of the eigenfunctions to come up with the coefficients for u. Okay, so we actually did this in a different video, I think. Here's our differential equation. But basically what I'm doing is I'm focusing on these first two terms, the one involving the f double prime and the f prime. I know that I can rewrite this as a product, p times f prime prime, using the same method that we used when we solved first order ordinary differential equations with an integrating factor. So basically, you need a 1 in front of the f double prime. I've already got a 1 there. Once you have a 1 in front of the f double prime, you look at the coefficient of f prime and you say, that's p of x. And your integrating factor, which will allow us to rewrite this as the derivative of product, if we multiply by that integrating factor. The integrating factor will be e to the integral of p of x dx. And in our case, we've got e to the integral of 2 with respect to x. And so we get e to the 2x plus c. That's infinitely many integrating factors. We only need one of them, so we'll just choose c to be 0. If we multiply by that, multiply the entire equation by this, where c is equal to 0, then the resulting expression for those first two terms will be the derivative of a product by the product rule. So we found the integrating factor. And then the p of x that I'm using here is not the same as that lowercase p of x. It's just the p of x I'm using here is the function in front of the f prime. Then we multiply the dE by the integrating factor. So what we'll have is f double prime plus 2 times f prime plus lambda times f equals 0. And I just left a little space for my integrating factor. So I'll have e to the 2x there, and an e to the 2x factor there, and an e to the 2x factor there. And of course, e to the 2x times 0 is just 0. So this is 0. And then this expression here is the derivative with respect to x of, it should be the derivative with respect to x of f prime times your integrating factor. In our case, that's e to the 2x. And check it out, make sure it actually works by using the product rule here. Here's our first function and there's our second function. According to the product rule, the derivative of a product is the derivative of the first, which would be f double prime, times the second, which is right there, plus the derivative of the second. The derivative of e to the 2x is 2 times e to the 2x. That 2 comes from the chain rule, and then we'll multiply by the first. So this is actually the derivative of this product. And I will write it in the reverse order so that it looks more like this. And we'll switch back to prime notation. This is e to the 2x times f prime plus lambda times e to the 2x times f equals 0. So if I'm looking at this and then I'm comparing it to the form of the differential equation in the regular Sturm-Liouville problem, I can see that the function multiplying f prime before we take this derivative is e to the 2x. So in our case, the function p of x is e to the 2x. Now to identify q, I'm looking for just the function times, or the function f that we're looking for in the differential equation times some other function q without a lambda. And I don't have a term like that. This has a lambda as a factor. So that's this right here. So q is 0. And the function multiplying f, and that's what we were looking for, is that e to the 2x. Notice that e to the 2x is positive. And that's necessary, it's required in order for this to be a regular Sturm-Liouville problem. That is the weight of the, when we say that those two functions f sub n and f sub m are orthogonal, they're going to be orthogonal with this weight. So it's very important that we find that weight. Okay. So what did we do? We wrote the differential equation in this form by doing all of this. So we compare to that form. And we identify P, Q, and sigma. And then once we've done all of that, we say, okay, that's enough to allow us to get started with finding the generalized Fourier series expansion, or the eigenfunction expansion for this function e to the negative x on the interval from 0 to 1. Notice that the function e to the negative x, it's just this function that looks like this. That function is continuous on the interval from 0 to 1. So when we say that this corresponds to this eigenfunction expansion, we actually use an equal sign there, because this series will converge pointwise to this because the function is continuous over the interval of interest. So now we will assume that u is equal to the sum as n goes from 1 to infinity of c sub n times f sub n. And I will actually substitute in my u. So I've got e to the negative x is my u. And I want that to be equal to the sum as n goes from 1 to infinity of c sub n times f sub n, and f sub n is e to the negative x times sine of n pi x. Now, you don't have to show this step, but sometimes it's a good idea just to remind yourself of what this means. I know a lot of my students need that reminder. This is c sub 1 when n equals 1 times e to the negative x times sine of pi x, plus c sub 2 times e to the negative x times sine of 2 pi x, plus c sub 3 times e to the negative x times sine of 3 pi x, and so on. Those are just sine functions of different frequencies. That just means we're going to see more of those little waves on a particular interval of interest as that number that's multiplying the pi x increases. And if you're curious about that, what do you mean by that? You might watch the videos I made about Fourier series. Okay, so e to the negative x can be written this way for some constants c sub 1, c sub 2, c sub 3, c sub 4, and so on, or in general, c sub n for n equals 1 to infinity. Our goal is to find the c sub n. In order to find the c sub n, we're going to take this equation right here and multiply that equation by sigma of x times f sub m of x. And first I'll say sigma of x times f sub m of x is this. Sigma was right there. We found it to be e to the 2x. Now f sub m of x looks just like f sub n of x. There's f sub n. But we're going to replace the n with an m. So I'll have e to the negative x times sine of m pi x. And of course, e to the 2x times e to the negative x, you just add the exponents because the bases are the same. It's going to give us e to the x times sine of m pi x. Okay, so we're going to multiply this equation by that. So we'll have e to the negative x times e to the x sine of m pi x. And that equals the sum, as n goes from 1 to infinity, of c sub n times e to the negative x times sine of n pi x. I'm just writing this down again. And then we're going to multiply each of those terms by e to the positive x sine of m pi x. Okay. And then we'll integrate, we're going to simplify this, and then we'll integrate over the interval of interest. And the interval of interest this time was 0 to 1, as stated here and also as stated here. When you add the exponents here, you're going to get e to the 0. So that's just going to be a sine of m pi x. We're going to integrate from 0 to 1. And then over here, the e to the negative x times the e to the x is just e to the 0 again. So those are gone. E to the 0 is 1. Now we could put the integral in front of the summation, but remember the integral of a sum is a sum of the integrals. So we can just pull that integral inside because we're just going to integrate each of the terms in the summation. Remember, this is actually this. So I'm going to multiply each of these guys by a particular function, the weight times the f sub m of x. And then I'll just integrate that piece and pull out the constant, and integrate that piece and pull out the constant, and integrate that piece and pull out the constant, and so on, which is the same as just writing it like this. The sum as n goes from 1 to infinity of c sub n times the integral from 0 to 1 of the following. This times this is e to the 0, which is 1. And then we have sine of n pi x times sine of m pi x dx. Okay. And then remember how this works. The integral from 0 to 1 of sine of n pi x times sine of m pi x, that's going to be 0 whenever n and m are not equal to each other. Otherwise, it's going to equal some particular value. And we'll find that through integration. Since this is 0 almost all of the time, again, you can imagine multiplying each of these terms by e to the x sine of m pi x, and then seeing sine of 2 pi x times sine of m pi x. Well, as m goes from 1 to infinity, we'll have sine of 2 pi x times sine of pi x, and sine of 2 pi x times sine of 2 pi x, and sine of 2 pi x times sine of 3 pi x, and so on. Whenever the m is not equal to 2, we're going to get 0. But when m is equal to 2, we're going to get something that's non-zero there. So all of these terms, because almost all of them are being multiplied by 0, are going to cancel, except for this c sub m term. So we're going to have c sub m times the integral from 0 to 1 of sine of m pi x times sine of m pi x, or sine squared of m pi x. And that's equal to this over here. Now, usually at this point, we switch from n to m, or m back to n. We'll see sine, or c sub n is this. It's going to be this integral. Oops, switching from m back to n, divided by this integral. And then we'll just evaluate the integrals. And again, what we're doing is we're simplifying using the orthogonality of f sub n and f sub m. And just recall what that means. It's just saying when we're in the interval of interest, 0 to 1 in our case, and we take f sub n and f sub m and we multiply by sigma as well, and we already have, we integrate, we're guaranteed to get 0 when n and m are not equal to each other, because that's what it means for those two functions to be orthogonal with a weight sigma. Okay, so now this is really simple. You just have to evaluate a couple of integrals and then divide, and that's going to get you the c sub n that you need. So let's do the integral in the numerator first. The antiderivative of sine is negative cosine. I've got negative cosine of a constant times x. When I differentiate, I have to multiply by that constant. When I anti-differentiate, I divide by that constant. Evaluate from 0 to 1. We're going to have cosine of n pi here minus cosine of 0. I'm just factoring this constant out and then evaluating at 1 and 0 and subtracting. And then I want you to recall, remember cosine looks like this. Just a cosine of x looks like this, or cosine of some angle looks like this, where my angle is on the axis there. When that angle is 0, we get 1. When that angle is pi, we get negative 1. And then at 2 pi, we get 1. And then at 3 pi, we get negative 1. And at 4 pi, we get 1. So this oscillates between 1 and negative 1. So this is 1, negative 1, 1, negative 1, 1, negative 1. Whenever we're plugging in or substituting an integer multiple of pi, that's how that behaves. So cosine of n pi turns out to be negative 1 to the n. When n is even, we get a 1, which is exactly what we see here. Cosine of 0 is 1, cosine of 2 pi is 1, cosine of 4 pi is 1, cosine of 6 pi is going to be 1. And then when n is odd, we're going to have a pi, 3 pi, 5 pi, and so on. We're going to get a negative 1. So this is just a shorter way of saying exactly the same thing. And of course, cosine of 0 is 1. So you've got -1 times -1 to the n minus 1. And of course, multiplying by -1, we could reverse the order there in the numerator. Okay, so that's the integral from the numerator. For the integral in the denominator, you have to use a power reducing formula from calculus 2. Now, some professors will actually let you use a table that will tell you the value of this. I believe there is a table in the Constanta partial differential equations text. But it turns out that this is true. Sine squared of some angle turns out to be 1/2 of 1 minus cosine of twice the angle. So this is 1/2, or the integrand is 1/2 of 1 minus cosine of 2 times n pi x, or you might write 2 pi nx. The order doesn't matter, right? Because it's commutative, that multiplication is commutative. Okay, so we've got this. I factored out my 1/2. Antiderivative of 1 is x. The antiderivative of cosine of an angle is sine of that angle. Since I've got a number inside, constant multiplying the x, if I were taking the derivative, I'd have to multiply by that constant. Since I'm taking the antiderivative, I will divide by that constant. Evaluate from 0 to 1. So we're going to have 1/2 times 1 minus this constant times sine of 2 pi n minus 1/2 of 0 minus 1 over 2 pi n times sine of 0. And sine of 0 is 0. So that means this whole expression is 0. And this is sine of multiples of 2 pi. And remember, sine looks like this. It repeats every 2 pi. So we're going to be at 0, and then we're going to be at 0. And then at 4 pi, we're going to be at 0. And at 6 pi, we're going to be at 0. It's always 0. So this turns out to be equal to 1/2. All right, so that means our c sub n is equal to the value of that integral in the numerator, which was this, divided by 1/2. And dividing by 1/2 is the same as multiplying by 2. So we have 2 times 1 minus -1 to the n, all divided by n pi. And so that means our e to the negative x is equal to the sum as n goes from 1 to infinity of the c sub n, which are given by that formula, times f sub n of x, which was e to the negative x times sine of n pi x. Now, if you want to, you could expand this just to get a better sense of what's going on. Let's see, when n equals 1. Now, if I'm solving the problem in my class, let's say for an exam, I would stop there and I would be done. But just to explore this a little bit more, let's expand it. And then let's look at the graph of e to the negative x and the graph of some of the partial sums of the series on the right-hand side. And we'll see that if we look at those partial sums, as we take more terms, we get closer to that function e to the negative x. So when n equals 1, we're going to have -1, or 1 minus -1 to the first. So that's going to be 1 minus -1, or 2 times 2. So it's going to be a 4 over pi times e to the negative x times sine of, if n equals 1, pi x. That's the n equals 1 term. Now when n equals 2, we're going to have -1 squared, which is 1. Then we'll have 1 minus 1, which is 0. So the n equals 2 term is just a 0. When n equals 3, we get this. We have a 3 pi in the denominator. In the numerator, we're going to have 1 minus -1 to the third. So that's going to be a -1. 1 minus -1 is going to be a 2. And then we'll multiply by 2. So we'll have a 4 there. times sine, or e to the negative x times sine of 3 pi x, and so on. When n equals 4, got negative 1 to the 4th, which is 1. 1 minus 1 is 0, so that's 0. And we can keep going, and I think I actually will. But before we do, I want you to notice the pattern. When n is 1, 3, 5, 7, anytime n is an odd number, I'm going to have a negative 1 to an odd power. So that'll be a negative 1 there. And 1 minus negative 1 will give me a 2. And then I'll have a 2 times 2 in that numerator. So I'm going to have a 4 in that numerator every time. And then in the denominator, I'm going to have that number n times pi. So I have 1 pi here, 3 pi here. The next one should be a 5 pi. The one after that will be a 7 pi. That's only when n is odd do we have that pattern right here for the coefficients. And then when n is even, this is going to be negative 1 to an even power. Negative 1 to an even power is 1. 1 minus 1 is 0. So that's why the n equals 2 term is 0. The n equals 4 term is 0. And it turns out it's going to be 0 for any time that n is even. So if I expand this further, it's going to look like this. E to the negative x is equal to 4 over pi times e to the negative x sine of pi x plus 4 over 3 pi times e to the negative x sine of 3 pi x plus 4 over 5 pi times e to the negative x sine of 5 pi x. And we can keep going. 4 over 7 pi times e to the negative x sine of 7 pi x. And that's the pattern. It goes on forever, just like that. We have infinitely many terms. And this said at the very beginning, when we first got started, that series on the right is going to converge to this function pointwise. It's converging to our function u of x because our function u of x is continuous on the interval. And remember, u of x is e to the negative x, and e to the negative x is going to look like this in general, and it's going to look like this on the interval from 0 to 1. Okay, so let's actually look at these functions and compare it to the graph of e to the negative x. So this is, this red graph here is the graph of e to the negative x on the interval of interest from 0 to 1. Now, if you want to, you could just graph the entire function. It's going to look like that. We zoom out, we see that familiar exponential function with a negative exponent there. It's decreasing as you go from left to right. It approaches y equals 0 as x goes to infinity. But again, we're just interested in the interval from 0 to 1. So we'll just type this here to the part of the graph that we're interested in. And then we'll zoom in a little bit so we can better see what's going on. Now, the partial sums of this infinite series here, that's what we found. They look like this. And I just wrote out the first 4 terms, but we could keep adding terms. I want you to see what those partial sums are. These partial sums, if you just take one of them, are supposed to approximate that function on the interval. So let's look at them one little piece at a time. Here's our first one. Now, if I'm just interested in the interval from 0 to 1, I think we can all see that this blue graph is not a very good approximation of this red function. But it's only the first partial sum. But we're not supposed to just take one of those. We're supposed to take a combination of them. So let's look at the second partial sum. That's the sum of the first 2 terms. Now we're seeing something that's a little bit closer to our red graph, but still at x equals 0, we get 0. At x equals 1, we get 1. That was actually a requirement of our eigenfunctions for the problem. But on the on the interior of that interval between 0 and 1, the function is getting closer to that graph, only taking 2 terms. Now let's look at 3 terms. A little bit better. You see how that purple graph approximates our function. 4 terms. 5 terms. 6 terms. Let's do one more. The next one involves n equals 13. So I'm calling that p sub 13 of x. So it's going to be the last one, p sub 11 of x, plus 4 over 13 pi times e to the negative x times sine of 13 pi x. And see, that's an even better approximation than the others. So if we just run through this, there's your first approximation, not a great approximation. The next one, a little better. Next one, a little better, a little better, a little better, a little better. And you can see, as you take infinitely many terms, as the number of terms goes to infinity, you're actually going to get that function on the interval from 0 to 1, which is pretty amazing, I think. And that's what we solved for. Okay, so the answer to this problem, the eigenfunction expansion problem, is this. Now, if you wanted to, because you have this 1 minus -1 to the n, you could rewrite this in a slightly different form, because we really only have odd terms here. Since we only have odd terms, I could rewrite this way. This is the sum as n goes from 1 to infinity of, let's see what. In the numerators here for our coefficients, we always have a 4. And the denominator, I've got 1 pi, 3 pi, 5 pi, 7 pi. The next one's going to be 9 pi. I've got odd multiples of pi. And I want the first one to be n equals 1. So I could write 2n minus 1 here. So that when n equals 1, I'd have 2 minus 1, which is 1, times pi. And then we'll have e to the negative x times sine of n pi x. But again, we're not getting all of the n pi, or we're not getting n equals 1, 2, 3 anymore. We're getting pi x and 3 pi x and 5 pi x and 7 pi x. So we're getting an odd multiple of pi x inside that sine function. And notice that this is a 7 pi x when that's a 7 pi. This is a 3 pi x when that's a 3 pi. So this is the this 2n minus 1 times pi. That's that odd number multiplying pi. And then don't forget your x. So I've got this is another form of the solution to this problem. This infinite series on the right converges to this. And I guess we should be a little bit more specific, not all the time. Just for x between 0 and 1. So that is our first example. Please let me know if you have any questions. I will post these notes online for you if you are interested.